So in the cancer data, we'll establish a cutoff value for classifying a patient as having cancer. So normally the cutoff value might be 50%. So if the test was above 50%, you would say they had cancer. And if it was below 50%, that would mean that the probability that they didn't have cancer would be above 50%, and then you would say that they didn't have cancer. But when we're talking about something like cancer, we probably don't want to leave it at 50%. We might want to bring it down to 20%. So if the probability that they have cancer is above 20%, we might say they have cancer. Or we might say the test tells them they have cancer. And if it's below 20%, then we would say that they don't have a cancer. So we basically just want to be able to adjust the cutoff value to measure or to reflect the importance of the two different types of errors. So in our previous discussion, we wouldn't have done this. Rather, we would compare the probability of cancer and not cancer, or not play and play, and chosen the one with the higher probability. So if someone comes in and the probability that they have cancer is, so we'd have two values for the class variable. They have cancer or they don't. And if the test said that there was a higher probability that they had cancer, then we would say that they have cancer. But here, we set a cutoff of, say, 20% for cancer, or going back to the other data, not play. Then if the probability of cancer is 20%, then even if the probability of not cancer is greater than 20% or greater than 21%, we still won't predict not cancer, but rather cancer. So even if this is down at 20% and maybe the other one, the not cancer, is 80%, we still may choose to do this because of the cost of making a mistake of telling someone they don't have cancer when they actually do. Thus, as a first step, we'll need to calculate the probability of the cancer class. We don't necessarily have to calculate the probability of the other class, because we check whether the cancer class is at least 20%. If it is, then we will say they have cancer. And more generally, if we're not talking about just two classes, or if we're not talking about cancer, we will need to calculate the probability of one class, which we'll denote C sub I, or so that could be cancer in this case, or could be not play in the case of the other data, or whatever the data set is. We'll calculate the probability of one of the classes given the values of the predictors, x1, x2, and so on. So we see that what we want is the probability of one of the classes given the values of the predictors. So once again, I'll state it again. If these are capital, that stands for the variables themselves. But if these are small letters, that stands for a particular set of values. So just to clarify that just a little bit more, if we had capital X's, we're talking about the variable outlook, the variable temperature, and so on, all of the different variables. But if we have small variables, or small letters rather, then we're talking about a specific value for outlook, like we might mean sunny, that outlook is sunny. We might mean that temperature is 80. We might mean that windy is true, and so on. So the small letters X indicate the actual values, or an actual set of values, whereas the capital letters just indicate the variables themselves. So here we're talking about the probability of a particular class given a set of values for the input variables. And now we will draw on Bayes' theorem. We just finished studying Bayes' theorem, and it's given below. And notice the switch here. So we said we wanted this, up here we said we wanted this, and notice that C is on the left side and this is on the right side, But remember what we said that Bayes' theorem will enable us to do, and that is to reverse these. So you have to recognize, and we pointed this out earlier, that this stands for one particular event. We said that each one of these is an event, but then that we have commas in there, and that means that it's the intersection of events, and we said that the intersection of events is an event. And so this stands for one event, and this stands for another, and then we know that Bayes' theorem allows us to switch them, to switch the order. So we do that here. So we put this on the left side and this on the right, and we fill out all the other parts of Bayes' theorem, and we get this. Now, if there are only two classes, so in other words, if it's like cancer and not cancer, then down here, we're only going to get two terms. But if there are three classes, then we'll get three terms down here. And if there are 10 classes, we would get 10 terms down here. But we saw the simplest version was when we had just two terms below here. So this would be one term, and then we just had one more term. We focused on that, although we did mention the general version like this. So again, note you may be confused by the fact that x1, x2, xp, that we have that. Remember that the comma means intersection, and the intersection of events is an event. So suppose we want to make the cutoff value just 0.2. So in the golf example, that would be, in other words, if the probability of not play is just 20%, then we will classify the day as a not play day. Remember we said that maybe they really want to focus on when people, even there's a small chance that people won't play. This sounds a little bit unreasonable, but doesn't sound like a great example. But if they wanted to focus on days when people weren't going to play, then they might say if there's even a 20% chance that people won't play, they're going to shut the course down. That doesn't seem very likely, but it was just for the sake of an example. Okay, but the cancer example makes more sense. In the example of cancer screening, we might say that even if the chance is only 20% that the patient has cancer, we will classify them as having cancer. Remember that if you classify someone as having cancer, that means that probably they'll go in for additional tests to see if there's, to sort of focus in on whether there actually is cancer. So it doesn't mean you're going to actually do something terrible to them just because you can't classify them as having cancer. On the other hand, if you tell them they don't have cancer when they actually do, then that could be a very high price to pay for that kind of error. So we may do this because we don't want to ignore someone who has cancer. So we may set it at only 20%. We realize that by making the cutoff value for when to classify someone as having cancer to as low as 20%, if we do that, we will probably classify many people who don't have cancer as having cancer. But that's the price that we're willing to pay in order to not miss finding someone who is actually sick with the disease. But for the sake of our data, I guess we could have had data in here for the cancer, but anyway, we don't. So going back to the play and not play example, going back to our example, the probability of not play, given that it's humid, we saw that that was given that it's humid, that was 50 out of 230, which is 0.22. So according to this cutoff rule, we would say that they are not going to play, even though it's only 22%. So with a cutoff of 0.2, we would say that this is a case of not play, even though the probability is only 22%. That's like we would say that even though there's only a 20% chance, the test only shows a 20% chance that they have cancer, we're going to classify them as having cancer. Recall that before, using the assign to the most probable class rule, if it was humid, we assigned the class play. So remember here we can see that if we went back to the original design of the rule, then since this is 180 out of 230, that's clearly the higher probability. So we would say assign the class as play, but because we're setting the cutoff at so low, we're going to assign the class to not play. Now we break from the digression and we return to our goal of understanding the naive Bayes classifier. We continue where we left off with complete Bayes. The previous example amounts to finding all the records, as we said, that are exactly like the new records we are trying to classify with regard to the predictor variables or values. For our new case, it was humid. Remember, we only had one variable in this data set, this made-up data set that we just looked at back here. This one up at the top there, we only have one variable. So for our new case, it was humid. So we looked for all the records in the training set where it was humid, and then either used the assign to the most probable rule or the cutoff rule. And if there had been other input variables, on the other hand, besides humidity, then we would have found the probability of that combination that matched our new record that were play, and the combination that matched our new record that were not play, and then chosen the one that is most probable. Okay, so what's wrong with doing this? So maybe we should just go ahead and do that. Use the complete Bayes. Why do we have to go any further? Why should we go to something called the naive Bayes? So what's the problem with this procedure? So there's a practical difficulty with the complete, or also called the exact Bayes procedure. What's the practical difficulty? So in the simplified golf example, there was only one predictor. It was humidity. But what if there were many predictors? And this is usually the case in data science. We don't have just one predictor. We want to consider data science problems with tens or even hundreds or even thousands of predictors. So sometimes in genomics, for example, or other applications, you'll have thousands of predictors. So not just one. Suppose we only had a modest number like 20 predictors. If each of those 20 predictors can take on, say, 5 values. So we had I think in our golf set, the maximum number of values we had was like 3. I think like the outlook variable could be overcast, could be cloudy, and rainy. So just 3 possible values for that one. But anyway, just let's assume that we have 20 predictors and each can take on 5 values. So that's not such an outrageous example. This is a conservative number. How many different sets of records are possible in that case? How many different combinations of these 20 variables and their values are possible? The answer is it's greater than 10 billion, because if you do the calculation, if you recognize how to do this calculation, you'll recognize that it's 5 to the 20th. So 5 times 5 times 5. So 5 to the 20th. So that's 5 to the 20th is 5 to the 20th is equal to 5 to the second to the 10th. So 5 to the 20th is equal to 5 to the second to the 10th. The 5 to the second is 25. So this is greater than 10 to the 10th. So this 5 to the 20th is greater than 10 billion. So anyway, how many different sets of records are possible? An absolutely huge number of records are possible. So with a modest number like 20 predictors, each have 5 possible values, it means that there are more than 10 billion different possible combinations of values. So what does that mean? Remember, we're looking for a match. So we're going to have some instance. It's going to be some set of values for these 20 variables. And how likely is it that we're going to find even one match? It's going to be like 1 in 10 billion, something like that. So that's very, very unlikely. So it's very unlikely we're going to find a match. If we can't even find one match, how are we going to find a majority class? So that's the problem. So how likely is it to have 2 records that are the same? if we have a relatively large data set, say 10,000 records, still it will be very unlikely. The probability of it happening will be close to 0. So that's the problem. So someone came up with a solution, and that is embodied in the naive Bayes algorithm. In the naive Bayes solution, we no longer restrict the probability calculation to those records that match the records to be classified. Instead, we use the entire data set. Before, our basic classification procedure was find all the other records just like our record, i.e. where the predictor values are the same, determine what classes they all belong to, and which class is more prevalent, and assign the record to that class, or classify that record to that class. The naive Bayes modification for the basic classification procedure is, so for the complete Bayes, it looks like this. Okay, so this is what we had before for complete Bayes. We just saw that 2 screens ago, I think. But with naive Bayes, it becomes, so what happens here? Whereas before we had this, now something changed. So what changed? This is still there, this is there, and this is here. So that's still the same. So what the part that changed is this becomes this. And then down here, the same kind of thing happens for these and all of these. But anyway, let's just focus on here. So what we can see is that this part here, from the P to this closed bracket here, becomes this. So how does that happen? Because it's not the same, right? This says P x1, x2, xp, ci. And now what did we do? We somehow broke it up into P x1 given ci, P of x2 given ci, P of x, and so on up to P of xp given ci. So somehow we change to here. And what is that? What are we doing there? Where might this come from? So before we explain it, stop the video and just try to rack your brain and see if this kind of rings any kind of bell at all with you. Okay, so let's see what this is saying. So for each class I, so if we're talking about the weather data, we would be talking about play or not play, so we choose one of them. So maybe we're talking about play, so CI would be play, or C1 would be play. And then find the individual probabilities that each predictor value in the record to be classified. So we're going to have some record which we want to classify. There are going to be a bunch of values for the predictor variables there, like x1 is the value of the first predictor variable, and x2 is the value of the second predictor variable, and so on. So anyway, each predictor value in the record, so here, given that it's play, what's the probability of the first predictor variable value? Here, given that it's play, what's the probability for the second predictor variable value, and so on till the end. For here, given that it's play, what's the probability of the last predictor variable value? So say the first predictor variable is outlook. So maybe in this particular case, outlook is equal to rainy. So given that the class is play, what's the probability that it will be rainy? And then this would be, given that it's play, what's the probability that it's going to be not humid? Suppose the second variable is humidity, and in this case it was not humid. So what's the probability that it's not humid? And we continue like that. So that's how we've changed the calculation. And then we multiply all of these together, multiply these probabilities times each other, and then times the proportion of records belonging to class 1. That's what this is. This is the probability of play. For example, if we're talking about the value of the class variable being play, then this is the probability of play. and that's just the proportion of the records that are play. And then we're going to do this for all of the classes. So repeat this and this for all of the classes. In other words, do this for the first class, maybe that's play, and then the second class, maybe that's not play. Or if it was cancer, do it for the first class would be, say, cancer, having cancer, and the second class would be not having cancer. And as many class values as there are, we have to do that for each of those class values. Do all of this for each of those class values. So repeat steps 1 and 2 for all of the classes. So we're going to then have calculated this for all of the classes. Or we're going to have for each of the classes, we're going to have this a value for this, because we're saying this is equal to this. So we're going to have a value for each of the classes, and then we'll be able to choose the class which is most likely. Estimate a probability for class I by taking the value calculated in step 2 for class I and dividing it by the sum of such values for all classes. In other words, actually we should divide by all of this. Assign the record to the class with the highest probability value for this set of predictor values. So for this set of predictor values, that's our instance basically. Okay, we still don't know where this came from though. Okay, so where did it come from? We have thrown in conditional independence as an assumption. So it's just an assumption, but we are going to assume conditional independence. And if you recall, we studied conditional independence, so we know what that means. We have to go back and review it and remember what the equation looks like for conditional independence. But you would say, well, who said that we can say conditional independence here? Well, no one says it. It's just that we saw earlier that it's going to be impossible to do the complete Bayes. For example, in the case where we have 20 variables with 5 possible values for each variable, we're never going to get a match. We're never going to be able to calculate probabilities for any of these classes. So we simply can't work with the complete Bayes. So someone said, well, let's make this assumption of conditional independence, because that will make the calculations much more likely to succeed or to be doable. So let's see what happens. The naive Bayes formula to calculate the probability that a record with a given set of predictor values belongs to class 1 in M classes as follows. Before we had this, with the assumption of additional independence, this becomes this. Okay, that's just repeating what we said already. So here is an expression of conditional independence, one that we saw. Remember, there were actually 2 versions of conditional independence. In fact, maybe we should go back and check that. So here they were. Here's one and here's the other. So this is R intersect B given Y, and with conditional independence we say that this is equal to R given Y times the probability of B given Y. And remember, intersection could be comma, so we could have R comma B, Y, and so on. And this was another version, but this one we're not going to use right now. So there it is, R comma B, or R intersect B, I think it was, slash Y becomes R slash Y and B slash Y. So this is conditional probability. Let's take that and go back and see that this is basically what we just did. I claim that what we just did is we had A comma B. Actually, we're going to have A comma B comma C comma 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 slash C, and then we're going to have A slash C, B slash C, and all the other ones slash C. So that's a more general form of this. So let's see if that's not what we had. So let's review. Let's say again what it is. What we're looking for. A comma B slash C becomes A slash C, B slash C. I'm leaving out the word probability here just to focus on what's going on inside the brackets. So let's check that. So there it is. This was A comma B. Then we had more than just B, but we had a bunch of them. But becomes A slash C1, B slash C1, and then there's more of them, so there's more here, till the end slash C1. So this is, going from here to here, is an expression of conditional independence. Okay? So we have assumed conditional independence. And that is going to make the calculations much simpler. We'll see that in a minute. But before we see that, let's just explain, what does this mean that we're making this assumption, or why can we make that assumption? Well, in some sense, we really can't make that assumption. But what we're going to do is use this to do classifications. And what happens is, it turns out that this method, this is a classifier basically. This calculation here is a classifier. It tells us this. So it tells us, given a set of inputs, what should we, what's the probability of this class, and what's the probability of all the other class values, and then we can choose which one. So that's a classification algorithm. So this is basically a classification algorithm. Turns out that even making this kind of unjustified, perhaps, assumption, still, this classifier does a very good job in practical problems. So if we're trying to predict in mail when something is spam or not, this does an excellent job. So that's kind of the justification. It works. Okay, maybe there's some reasons why we could say that things are conditionally independent, but we won't try to make that argument here. I don't think that that's really what actually happened. I think that what actually happened was that this was just impossible to do. Someone said, well, if we assume conditional independence, we get this. And this turns out, as we're going to speak about in a moment, this turns out not impossible to do. Okay, so why is that? So why is this lower calculation here considerably easier to do than this calculation here? So this calculation we already explained, we're very unlikely to find a record that matches our given record, our new record, the record we need to classify. And that's because we have to match all of these conditions. For example, suppose this is that it was rainy, and it was humid, and the temperature was high. And if we had many of these restrictions, we're not going to find many records that match them exactly. So that's quite difficult to find such a record. However, look at this. This has terms like this and this. In other words, terms like this. So, or if we want to be specific, terms like this. So this says, find the probability given that we are working with not play records. So from within the entire data set, we are working with not play records. What is the probability that those records have outlook equal to rainy? So that's not very restrictive at all, much less restrictive than saying outlook has to be rainy, and humidity has to be high, and temperature has to be low, and all of these. So this is much less restrictive, and so we're much more likely to find cases like this. And then this would be for a different variable. This might be for humidity equals high, and this might be for temperature equals low, and so on. But each one of these is much more likely to occur, and so we're much more likely to be able to calculate these. Whereas this, as we said, we probably won't even find one case that will match our record exactly. So whereas this was going to be very hard or impossible to find, these will not be hard at all to find. And that is why the naive Bayes is calculatable, whereas the complete Bayes is not.